Hello everyone. Thank you all for coming. I'm Mats Kirkaune. I'm a PhD candidate at the Rossland Center for Solar Physics at the University of Oslo, and I've been involved in the AtLAST Solar Stellar Working Group for some time now, and will present some of our findings in looking into the solar science case for AtLAST. The title of my talk is Prospects for Observing the Sun with AtLAST, and it is roughly divided into four sections where we will spend the vast majority of our time on the first three main sections. We will start with why the sun should be studied, its importance for us on Earth, and why we need to understand it better before moving on to the connection to AtLAST and the various solar science cases that have been identified for the AtLAST telescope and how AtLAST could contribute to solving those cases. And the third and last of the major sections is that of simulating solar observations with AtLAST, where I will show some example simulations of a AtLAST observation of a solar flare, and then at the very end we will have some conclusions and outlook. So why study the sun? So I guess everyone knows the sun. The sun is always there when you go outside, at least if it's sunny. But the sun is so much more than the seemingly boring white light bulb in the sky that appears to be more or less steady. This sun is everything but a steady astronomical object. As you can see in this observation in the ultraviolet, this observation covers almost 3 days at the end of March of this year. You can see that the sun is a very, very active and very, very dynamic object it is essential for life on Earth by providing us with much needed light and heat, but it can also act up and cause various disturbances that we'll look at. The sun is a big ball of plasma or ionized gas, where we have a lot of highly complex magnetohydrodynamic processes that move this plasma around, follows the magnetic fields of the sun, and you have various activity phenomena. And that makes the sun itself a very important plasma laboratory. The study of the sun is very important for plasma physics, where you can study how plasma interacts with magnetic fields in different environments in its natural habitat, if you can call it that. The sun is also a very important reference star in stellar astrophysics, as it is the only star that we can resolve at least well. So it is a very important reference when studying other main sequence star and especially sun-like stars. As I mentioned, the sun hosts a lot of different activity phenomena, and these phenomena can impact life on Earth in a major way through the disturbance of critical technologies and infrastructure. And one such activity phenomena is that of coronal mass ejections, which you can see an example of here, where we can see enormous amounts of plasma or ionized gas being flung into interplanetary space, very, very far from the sun itself. And these waves of plasma or ionized gas can travel far into the solar system and can hit the planets. This is an animation from the Space Weather Prediction Center showing the predicted trajectory of a coronal mass ejection moving out from the sun here in yellow and the Earth shown in green. They are not to scale, but you can see at the top row showing the plasma density that the coronal mass ejection in this case actually hits Earth. And as these highly energetic solar particles hit Earth, they can have a lot of effects. Probably the most well-known of which is the aurora, both the northern and southern lights, There's an example of which from northern Norway, where you can see that the energetic solar particles have ionized elements in the terrestrial atmosphere, and you can see these beautiful streaks of green and purple following Earth's magnetic field. But they can have a lot of other effects as well, most of which are not as beautiful. This is an infographic from the European Space Agency showing a selection of the different technologies that can be affected by solar activity through space weather. So we have satellites here, the coronal mass, the solar particles can increase the friction for satellites, causing satellites to fall down, which has happened in the past, for example, with SpaceX satellites. It can ionize Earth's atmosphere, hindering radio wave communication. You can have induced currents in power systems, knocking out entire power grids and transformers, causing the loss of electricity and on large parts of the Earth, which could be critical for critical infrastructure such as hospitals and the like. But it can also be more directly dangerous for crew and air passengers. It's not uh, dangerous to fly once in a while through a solar storm, but it's more important for crew and pilots that regularly fly through polar regions where you can have such effects, and especially for astronauts being well outside Earth's atmosphere and in some cases outside Earth's magnetic field as well, and can be very, very exposed to space weather events. This is especially relevant now as we speak. There are astronauts well outside of Earth on the way back from the moon now, and they would, of course, be very, very exposed to any major space weather event if something like that were to occur. So we have now looked briefly at why we should bother about the sun. It has an enormous impact for us in our day-to-day lives. So what's the connection to AtLAST in all of this? And what solar science cases could AtLAST help to address? So as I mentioned, and you saw in the UV image in the very beginning, the sun is all but a white, steady light bulb in the sky. The sun has a lot of different structures which you can probe with observations at different wavelengths or frequencies. So all of these observations are of the sun, but at different wavelengths or frequencies. You have at the top right here, you have observations in the ultraviolet from the Solar Dynamics Observatory. You have the visible here shown as the white light continuum, also from the Solar Dynamics Observatory. And the rest of these are all in the millimeter and the radio. So you can probably recognize ALMA here at least at shown as full disk ALMA total power maps of the sun at 230 and 90 gigahertz. So if you add AtLAST to this, it would have covering its frequency range from 30 to 950 gigahertz. It would overlap the frequency coverage of ALMA, but at least not as of yet. ALMA does not offer solar observations at its highest frequencies, but that is something we would hope AtLAST would provide at least. So we would have to extend its range far outside of this plot. And it is really this multi-frequency or multi-wavelength view of the sun is really critical in studying different phenomena on the sun, as you ideally simultaneously would like multi-frequency detections to probe different heights to really see how the phenomena that you observe span different heights, how they look below or above for heating mechanisms and the like. So as part of the first AtLAST project, AtLAST 1, there were some white papers written for each of the major science cases, and there was also one written for the solar and stellar science case, published in Open Research Europe in 2025, where 5 key solar science cases were identified, which AtLAST could contribute to. And I'll go through most of them now briefly, just to look what exactly it is AtLAST could do to further these cases. So that the first of which is the thermal structure and heating of the solar atmosphere. So probably the biggest still unanswered question in solar physics, if not astrophysics, is that of the atmospheric heating problem, which is also referred to as the coronal heating problem in many cases. So as you may know, the solar atmosphere is divided into 3 main parts. The photosphere, which is also referred to as the surface in many cases, is the bottommost layer of the atmosphere. Then you have the chromosphere above it, shown in this temperature plot in the bottom left. And then you have the corona, the outermost layer of the atmosphere at the very top. But what is very counterintuitive when it comes to these atmospheric layers is that the photosphere is actually the coldest. So as you move up from the photosphere into the chromosphere, you initially have an increase in temperature, which is not something you would expect moving away from the nuclear fusion processes in the solar interior that generates all this energy. Why would the energy increase? And as you move further up to the upper chromosphere, you get to a transitional layer called the transition region, where the temperature increases drastically as you go up to the corona. And in the corona, you even see temperatures on the order of 1 million Kelvin or more, depending on the activity level. And the reasons for which are not entirely known. There are several candidate processes that have been proposed that could help drive coronal heating, but the relative importance of each phenomena is still unknown, and that's partly why we need further observations of the solar atmosphere, and especially the chromosphere and the corona, where the different heating mechanisms would leave their imprint. And that is where AtLAST comes into this. With AtLAST's frequency range from 30 to 950 gigahertz, the heights at which it would probe would all lie in the chromosphere. So this yellow bar shows roughly the probed heights of AtLAST. So it would be a nice instrument for observing the chromosphere and any heating mechanisms that either transport energy from deep in the photosphere and out through the corona, up through the chromosphere into the corona, should leave some imprints in the chromosphere. So as the chromosphere itself is also heated, we also expect to see heating events in the chromosphere, and therefore it will ideally like chromospheric observations to try and pinpoint those heating mechanisms and their relative importance. When it comes to heating mechanisms, one advantage of observing in the millimeter regime is that the measured brightness temperature is linearly dependent on the actual local plasma temperature. So as you map the solar chromosphere at different frequencies, you get an actual map of the local plasma temperature across the chromosphere. And then if you have a true multi-frequency instrument at last, which could produce simultaneous multi-frequency maps, you would actually be able to map the thermal structure across the chromosphere. And depending then on how many frequency bands you would be able to observe simultaneously, get a very, very accurate 3-dimensional map of the thermal structure of the chromosphere. And another advantage is that of having polarized observations, which you could use in reconstructing the line of sight magnetic field, and through inversion codes use those line of sight components of the magnetic field to reconstruct the actual three-dimensional magnetic field as we move across the chromosphere. And if you then map at multiple frequencies across the chromosphere, you both get a thermal and magnetic field three-dimensional map of the chromosphere, which would yield invaluable information about any heating mechanisms that go on. So the second solar science case that was identified in the white paper was that of the solar activity cycle. So as you may know, the sun goes through an 11-year cycle where the polarity of its magnetic poles flip. So starting out at the right here, you have the sun at close to the solar minimum. So you have the two poles very nicely opposed, one in the north, one in the south, and you have a very simple magnetic field, not that different from that of a simple bar magnet or a dipole. And you see very little structure at that point. You see very little solar activity, and that's why you call that period the solar minimum. But at the halfway point between the two poles clipping, the magnetic field is much more complex. And as you can see on the left here, no, the right, sorry, um, you have a lot more of a complex magnetic field, and you have a lot more bright points, and you have a lot more solar activity as the magnetic field is a lot more complex. You have a lot more reconnection. You have a lot more magnetic stress, and you observe a lot more solar activity phenomena. And yes, this is observed with the Solar Dynamics Observatory here seen. And the solar activity cycle is also seen in ALMA total power data. Here you can see two full disk maps, both in the ALMA band 6. The one on the left being closer to solar minimum, and the one on the right closer to solar maximum. And in the leftmost plot, you see a lot less structure, while on the right, you see a lot more bright and therefore warm structures here as active regions. But solar observations with ALMA are few and far between, so it's hard to reconstruct a full evolution of this millimeter sun across the solar cycle. And that's where we hope AtLAST could greatly contribute to that, to studying the solar activity cycle. AtLAST with a 50-meter aperture would naturally produce images with a lot higher angular resolution than that of ALMA total power, more than 4 times better actually, at 220 gigahertz, which falls in band 6. ALMA total power has a resolution of 28.6 arc seconds, while AtLAST would be less than 7 arc seconds at the same frequency, and with the same advantage as that we saw for the thermal structure, having truly simultaneous multi-frequency maps, and therefore being able to map the thermal structure and how that evolves during a full solar cycle from minimum to the maximum and back to the minimum would yield a valuable input in how the solar activity cycle manifests in the millimeter regime. And that's why we hope to, at least by being involved from the very beginning, hope to be able to set aside some time, at least weekly or hopefully daily, to have periodic and very frequent full disk millimeter maps to really see how the different structures evolve in the millimeter regime as the solar cycle evolves. So the third science case that was identified was that of solar prominences. So solar prominences are large structures of relatively cool chromospheric plasma of the temperatures of around 10,000 Kelvin or less that is extended far into the solar corona, which is much, much hotter than that. And it's supported both against gravity, so from collapsing, and shielded from the surrounding much hotter corona by a complex and twisted magnetic field. So you can see one such example of a solar prominence here on the right, where you can see how big these structures can become. This is extended off the solar limb, and the Earth is here shown to approximate scale. But as these structures are so closely connected to a complex magnetic field, these fields can ultimately become unstable, causing the prominences to erupt, which is often associated with coronal mass ejections and are themselves important drivers of space weather as they throw out these hot ionized gas far into in interplanetary space. So understanding these um, phenomena is important for space weather reasons as well. This is an example of an erupting prominence here in the ultraviolet and the visible, where you can see the initial loop structure uh, on the solar limb, and then how it ultimately becomes unstable and erupts, flinging the ionized gas of plasma into interplanetary space. And this is actually the same prominence eruption that caused the coronal mass ejection that I showed a video of in the introduction. So how could AtLAST contribute to this? It's more of the same advantages as for the last two previous science cases, having multi-frequency and polarized observations would really give you a nice idea of the thermal and magnetic structures of the prominences. And if you have uh, uh, high temporal cadence observations across the entire lifetime of the prominence, so from its formation until its eventual eruption or dissipation, could really get invaluable insight into how the structure of the prominence uh, evolves as the prominence itself evolves. And for this, AtLAST could be very helpful. So yes, the fourth and the final major one I'll present science case is that of solar flares. So as you may know, solar flares are caused by reconnecting magnetic field lines in the sun, where magnetic energy is so where the magnetic field line reconnects to more favorable energetic configurations and therefore releases enormous amounts of energy into the surrounding atmosphere, heating it, and which is observed as these brightenings. So here you can see an example of such a flare on the limb here. So solar flares occur on many, many different scales. You have the most powerful flares are called X-class flares, which you see an example of here. But you also see much smaller flares down to micro flares, and even the hopefully the famous or infamous nanoflares at even smaller scales than that, thus releasing less energy, but still contributing to heating. So as I mentioned, yes, you have many different scales. This is an X-class flare, and X-class flares release on the order of more than 10 to the 25 joules into the surrounding atmosphere. And that is equivalent to hundreds of millions, up to billions of nuclear bombs, or if you prefer a more positive comparison, that's equivalent to around 100,000 times humanity's annual energy consumption. And um, these flares are also sometimes associated with CMEs and are therefore themselves also important drivers of space weather. So understanding these phenomena is important also for space weather reasons, but it also for for other stars, it's important to study solar flares, as flares are also observed on other stars, sometimes much more powerful than what the flares that we observe on the sun. So understanding solar flares is also important for studying extrasolar space weather and in connection to exoplanet habitability, especially, and that's the solar stellar connection, which is actually was identified as the fifth major science case for AtLAST. Sorry. Just have to go through this again. So how could AtLAST contribute to this? Flares are notoriously hard to predict. There do exist some flare alarms at telescopes, but for a flare alarm to be triggered, the flare itself must have started to actually trigger the alarm, causing you in many cases to lose out on observing the initial phases of flares. And also, if you want to observe flares with small field of view instruments, such as an ALMA interferometric mode, you need a high degree of luck to be able to have a flare go off within your limited field of view. And this is where we think AtLAST would make a great change if we make use of its large field of view in combination with fast scanning. We have seen that AtLAST should be able to produce full disk maps of the sun at a relatively high temporal cadence. And if you then just perform such full disk scans without actually targeting flares, you do capture flares serendipitously, so by chance. And if you then just have a scheduled 1 hour AtLAST observation covering the full disk, you would capture all the flares that would go off in that time window, assuming they are above the sensitivity limit of the telescope and that you can resolve them. So AtLAST would really be great for capturing all the phases of a flare, as you would not lose out on even its initial phases. So the final main section that I'll go through is that of simulating solar observations, where I'll show an example simulation of a solar flare that we have performed. So to even be able to simulate AtLAST observations, we made use of the Maria simulator, which has already been presented twice in the AtLAST forum, so I won't go into the nitty-gritty details. So see the AtLAST forum talks by Joshiva and Thomas for the details, but just a recap, the Maria simulator is a multi-purpose submillimeter telescope simulator and can be used to test out different instrumental setups and scan strategies to really test out how you best could use a new facility for observations and for observing different targets at different seeing levels, as Maria actually applies a realistic and evolving terrestrial atmosphere, which you can tweak the parameters of yourself to simulate observing under different seeing conditions. So this is just a very rough outline of how this works. You supply an input image or an input movie if you want to simulate observations of a dynamic target such as the sun. Then you define an instrument and a scan setup. You define the parameters of the terrestrial atmosphere that you want to apply, and then you simulate your scan with your defined instrument, creating a synthetic observation, as you can see an example of here. But we then meet the problem of what do we use as an input image, because ideally you would use a high resolution depiction of the true millimeter sun to do this, but no such observations exist at a sufficiently high resolution across the full disk. And that's why we need AtLAST to create such observations. So we had to construct our own input a map or input movie in this example case. So to do this, we took actual full disk millimeter maps from ALMA, here from showing one such observation in band 3, and then compared it to what the sun looks like in the ultraviolet, here from the 304 and 1600 angstrom channels from the AII instrument at the Solar Dynamics Observatory. And then we can see there are similarities in some of the structures observed. And we then ended up creating a fake millimeter sun by combining these two UV channels, for scaling the UV intensities to match the actual millimeter brightness temperatures observed in the actual ALMA data, and applying artificial limb brightening to mimic the true millimeter data as closely as possible. So that ended up looking like this. So now you have the actual ALMA total power observation on the left and the constructed fake millimeter sun on the right, where we have taken full advantage of the high resolution that we can achieve in the ultraviolet. But there's another advantage in the AIA data from the Solar Dynamics Observatory, namely that of also a high temporal cadence. So this is now no longer a map. This is an evolving cube which evolves in time. So we have this evolves with a temporal cadence of 24 seconds from the 1600 channel. And in this input cube, you can actually see an intermediately sized flare that goes on in this active region down here. And we wanted to see if we could simulate AtLAST observations that would actually be able to resolve this flare both in space and in time. So now we have an input map. What about the instrument and the scan? The instrument in this example case took inspiration from the AtLAST memo number 4 in the AtLAST memo series, where it is mentioned that the first generation AtLAST instrument should be able to have around 50,000 pixels per band. And then we chose a field of view of 8 arc minutes in this case, which is quite big, which a first generation instrument should be able to fill up to 400 gigahertz. But a more reasonable instrument, but a more ambitious but still reasonable instrument with up to 150,000 pixels should be able to fill that even all the way up to 700 gigahertz. So still not taking advantage of the full frequency range of AtLAST, but still covering an impressive frequency range. And that such an instrument would be well within the second generation estimates for an instrument. And for the example simulations, which I will now show in just a few minutes, we only simulate the 2 lower bands for computational reasons. They are centered at 93 and 220 gigahertz respectively, which is equivalent to ALMA band 3 and band 6, if you're familiar with ALMA. So we have an instrument, then what about the scan? So in the scanning, we take inspiration from how ALMA scans the sun using its total power antennas, using a traditional double circle pattern here seen on the left in right ascension and declination in this nice spirograph pattern. And on the right, you can see the same scan pattern, but now in azimuth and elevation, showing that as we scan in time, you are able to you follow the solar disk center and are able to complete many such double circle patterns, creating one full disk image of the sun for each completed double circle pattern. And in this case, which is not very, very well optimized, we can probably push it a bit further. But in this example case, one such double circle pattern is finished once every around 35 seconds, which is still an amazing improvement over almost 10 to 15 minutes at the same frequencies and at a worse resolution. So now I have an instrument and a scan. I don't have a separate slide for the atmosphere, but the atmosphere is initialized in the Maria code directly by choosing a site, which is here chosen to be the China Antwerp Plateau, to be as close to where AtLAST would be in the future as possible. So then we have everything we need to create synthetic observations, but how do these look like? So here you have the resulting full disk, now time evolving simulated AtLAST observations at 93 and 220 gigahertz, showing the full solar disk at a cadence of 35 seconds. So you can immediately see that as you increase the frequency from 93 to 220, naturally the angular resolution improves. But you can still, in the 93 gigahertz map, you can recognize a lot of the active regions, and you can really see some of the structures quite well. But maybe what is most interesting here is that in this black box, you can actually see that the flare is captured both in space and time. So you can actually make out the flare quite well in both cases, and even better if you zoom in. Is this? So now we have zoomed in to the black box covering the active region where the flare occurs. So you have the 93 gigahertz case at the top row and the 220 gigahertz case at the bottom row. And you can really see that the flare is captured well. You can make out the structure of the active region and the flare itself. And if we look at the light curve on the far right, you can see the 220 case in red and the 93 case in black. You can really see that we have quite a few measurements in time, and you can actually see the temporal evolution of the flare quite well. But of course, this is based on constructed data. This is not true millimeter maps. So this is probably not what this would look like in true millimeter data, but just an example of what kind of data AtLAST could actually produce. And this is not something any current millimeter facility could do, and this would really be transformative for the solar and the solar millimeter community especially. And just a bonus of doing non-targeted observations is that as you don't focus on a small region on the sun, you capture everything that is interesting that goes on, such as in this case, where not only do we capture the flare in this active region, we also capture a prominence of limb in this blue box here. You can't see it in a linear temperature scale, but if we go to the log scale shown on the right, you can really make out the structure of the prominence here at 220 gigahertz. And as this also evolves in time, you can see how the prominence itself evolves, which is also cool to see. So just as a conclusion and outlook, we have seen that both in simulations, that we have shown that AtLAST could produce at least relatively high cadence multi-frequency full disk maps, which would be And if you do that at many frequencies at the same time, you can be able to reconstruct both the thermal from the temperature itself, but through having polarized observation, also the magnetic structure across the chromosphere, creating detailed three-dimensional maps of the temperature and magnetic field across the chromosphere, uh, producing data which is not produced by any current or at least that I know of planned millimeter solar capable facility. Uh, such and as such, AtLAST would be highly complementary to other solar and solar capable instruments that are currently operational and that will be operational by the time AtLAST is built, would be highly complementary to ALMA itself, but also to the Square Kilometre Array in South Africa and Australia, but also the European Solar Telescope to be built in the Canary Islands of Spain. As we have seen, non-targeted full disk mapping is great for capturing highly dynamic phenomena that are hard to predict, such as the solar flares. And I believe that AtLAST could really produce some data that will be very, very useful to the solar community, not just the solar community that works in the millimeter, but the entire solar community. And it is obvious that AtLAST would be highly transformative for the solar physics community. And yeah, I think that's it. Thank you.